Okay guys, so this last tutorial is on reaction rates, something you've probably just covered recently in class. So let's get straight into it. I'll just hide that for now. Alright, so guys, reaction rates. What does this term reaction rate actually mean? Wow, reaction rates, let's get into it. What is reaction rate? It's basically just how fast or how slow a reaction takes place. So a fast reaction rate or a high reaction rate is a reaction that occurs very quickly, or a slow or a low reaction rate is a reaction that takes a very long time. But we can actually do some things to speed up or slow down a reaction. So let's look at some factors that we can change to affect reaction rate. But before we do that, we probably need to understand a little bit more about how a reaction works. So I'm going to go over some things that aren't assessed. And it's going a little bit beyond what you'd need in your test and things like that. But that's, I think, important because I really would like you guys to try, if you can, to understand why some of these things affect the reaction rate. And that understanding, I think that's what science is really about. It's trying to understand how and why things work the way they do. So even though it's not going to be assessed, if you can figure it out in your head, it's going to really help you when you go into the senior levels. So, this is all based on collision theory. Now, like I said, don't freak out. If you didn't hear about this in your class, that's fine. You're not going to be tested on collision theory. Collision theory is not going to be in the test. You don't have to know the term or the name. But it helps to explain why the reaction rate is at a certain rate. So, guys, collision theory states that a collision must happen for a reaction to take place. So, reactants must collide in order for the reaction to occur. Now, the energy and the orientation of the reactants determine if a collision is successful. So the energy is how fast they're moving. So think about a collision in a car. If you're driving a car, a low energy collision would be just a little bump. You weren't moving very quickly. A high energy collision would be you going 100 k's straight into a wall. That would be a really high energy collision. Orientation is just which way they are facing. Alright, so let's have a look at that. Here we've got a little video, and I'll play that again in a second. So it just shows here we've got some reactants, the blue and the red thing here, and they're going to undergo a collision, and a successful collision will mean that they react and bond or join together. Alright, okay, let's play that again. So you can see there the first couple of collisions just weren't quite successful. The orientation just wasn't quite good enough for them to actually react. So guys, a successful collision, a successful reaction takes place when there is enough energy, we call this activation energy, to get the reactants to collide and react together. So sometimes we need to give a chemical a little bit of energy, some of our reactants, enough energy that they can actually collide together with enough energy fast enough that they'll actually bond together. So this is actually the minimum amount of energy that it takes for a reaction to occur. Now think of every time you light a Bunsen burner. Every time you light a Bunsen burner, you need to light it with a match. But once it's lit, you don't need the match anymore. It burns all on its own. That's because gas reacts with oxygen, and when it reacts with oxygen, it produces heat energy, which can make more of the gas burn, and it kind of carries on in a chain reaction. But if you turn on the gas without lighting it, the gas particles and the oxygen particles in the air just aren't moving quite fast enough to actually react together. So they'll bump into each other maybe occasionally, but they just don't have enough energy to actually bump into each other and stick together. So the match just heats them up, makes them move a little bit faster, alright, so that they have enough energy to actually collide and bond together successfully. And as soon as one or two of them do that, they release energy, and that energy gives some of the other molecules the energy to bump into each other and react or collide successfully, and so a chain reaction starts to happen. So as we need a little bit of energy to get the gas particles to collide and react with the oxygen, but once they've done that, they give off the energy to get the next ones to do it, and then they give off the energy to get the next ones. We get a chain reaction, and it keeps going all by itself. So it's a little bit like this boulder here. We need to put in a little bit of energy to get it up to the top, but once it's up there, then it'll start rolling all by itself. So with the reaction, the match, we need a little bit of energy to give those particles enough energy to collide successfully, but once they do, they'll actually release energy and make the other ones collide, and it'll carry on all on its own. Okay, so now that we know a little bit about that, and like I said, those last few slides, the collision theory stuff, isn't going to be assessed. You just need to know some of these ways to speed up a reaction. But I think it would be really fantastic if you had an idea about why these things actually speed up the reaction. Like I said, it's not going to be something you're assessed on, it's not going to be in your test, but I just think it's great. If you've got that understanding, for me that's what science is really about. So, first way to speed up reaction, it's particle size. The larger the particles, the lesser the surface area, and the longer it will take to react. The smaller the size of the particles, the more the surface area, and the lesser time it takes to react. Now I want you to think about this. Imagine we are the reactants, and imagine we're in the gym, the school gym, and we're all running around blindfolded, and when we bump into each other face to face, then we'll react and we'll form a bond, and we'll join the person we bumped into. Well, if I tie you together in groups of 4 or 5, if I take our class and tie you together in groups of 4 or 5, it means that there's only 4 groups running around, and it means if you're all tied together back to back, or side to side, then the particles really can only bump into you from the front. So there's less surface, there's less areas or less angles from which the other molecules can approach you, because some of them are all, you might all be back to back, so those are all hidden in the middle of your group. So if we break up the particles, if we split the class into individuals, so we untie you and you're all individuals, and we blindfold you and you all run around until you bump into each other and react together, you're much more likely to react, or you'll find someone or bump into someone. It'll take less time, you'll bump into them more quickly as an individual, because there's more bits around you and there's more surface area. You can bump into them from all sort of sides, so there's a greater chance you'll actually react or bump into those other particles. So guys, that's basically the same idea of, if you may have done an experiment where you had a lump of iron, so just like a nail, or some iron filings, sort of small tiny pieces. Small tiny pieces means there's more surface area. There's kind of, think of it like that example, we've split up the groups into smaller groups or even individuals, and that just means there's more likely to be successful collisions, people bumping into each other and forming bonds. Temperature. When we increase the temperature, the kinetic energy, now you probably don't know what that word means, don't worry about it. When we increase the temperature, the kinetic energy increases, which will make the particles move even faster. And that's what kinetic energy is. It's just how fast something's moving. And it also takes into account how heavy it is. So things that are heavy and moving fast have lots of kinetic energy. But in this case, we're really just talking about how fast things are moving. So when we heat things, the particles move faster. And actually, when you measure the temperature of something, what you're actually measuring is how fast the particles in that substance, that material, are moving. Isn't that crazy? When you measure the temperature, you're actually measuring how fast the particles in that substance are moving. So when we heat something, the particles move faster. When we cool it, they start to move slower. So guys, if the particles are moving faster, so again, use our example, we're all the reactants in the gym, running around blindfolded, and if we bump into each other, we might react and form a bond, form like little pairs or something like that. If you're moving around really slowly, it'll take a while before you bump into someone and form a bond. But if we're all running around really quickly, then we're going to bump into someone pretty soon, pretty quickly, and we're gonna react much sooner, and so the reaction occurs faster. Concentration. Concentration is how concentrated something is. Now, you've probably all made juice or cordial from like sachets or from like a cordial syrup. And guys, that's a good example of how concentrated something is. If you pour in a lot of syrup and hardly any water, it's really concentrated. If you add lots of water, it's going to be much less concentrated, or dilute. So dilute is kind of the opposite of concentrated. All right. Now, the more concentrated your reactants or the particles are, the more chances there are of colliding. So think about that. If we went into the gym and we put a whole bunch of, if we took 5 classes instead of just the one, you're more likely to bump into someone. Or even if, rather than adding more people, even if we just went into a classroom instead of the gym, if we were in a smaller space, it would probably be more likely that you'd bump into someone and react with them, because there's less space for you to move around and you're more concentrated. So again, the more concentrated you are, the faster the reaction will occur. Now, the last one, catalysts. Catalysts speed up a chemical reaction. So the catalyst is not a reactant, and it is not used up. So catalysts help a reaction to occur, but they're not actually used up. You may have done an experiment in class where you had manganese dioxide and you added hydrogen peroxide, and the manganese dioxide is kind of the helper, which helps hydrogen peroxide break down into water and oxygen. Now, if you look at hydrogen peroxide, the formula is here H2O2. It's basically a water with an extra oxygen attached. And so manganese dioxide just helps it to release that extra oxygen, and so we get liquid water and oxygen. And the oxygen forms in the form of sort of a foamy or bubbles often coming off that solution. So guys, manganese dioxide is what we call a catalyst. It speeds up a reaction, but it doesn't actually get used up itself. It's a helper. So imagine in our example with people running around, imagine we've got a few matchmakers, a few people running around, helping to pair people up to make it happen a little bit quicker. So some catalysts work by helping the reactants to combine at the right orientation. So remember, if they bump into each other sort of face to face, they're more likely to react or combine. So sometimes a better orientation means they're more likely for there to be a successful collision. But there are other ways in which a catalyst can work too. So guys, again, you're not really expected to know how these things work, but if you've got a bit of an idea, I think that's really great. So in summary, guys, to speed up a chemical reaction, we can change the particle size. So a small particle size gives us a faster reaction. We can change the temperature. A higher temperature gives us a faster reaction. We can increase the concentration. The more concentrated, a faster reaction. Or we can add a catalyst, a helper, to speed up the reaction. Okay, so guys, that's basically it for reaction rates. And again, I hope that really did help. Guys, good luck for your test. I hope you can do some decent revision. So good luck.